Hello there, WINDPOWER students. Dr. John Troggy here, and we're going to keep plowing our way forward through this module of the course that's about wind profiles. And we've already talked a bit about the log wind profile, and today I want to talk about two other wind profiles that are not really discussed in your textbook. That's why I've provided you that extra reading. If there's a link to it on the introduction to this module, and if you can't find it, please let me know. Now, so far we've learned a lot about the role of static stability in the atmosphere. We saw slides like this one that's showing how when a layer of the atmosphere is statically unstable, once you lift an air parcel, it will become positively buoyant and continue to rise on its own. Or, if you lower an air parcel, you nudge it downward, it will become negatively buoyant and sink on its own. Notice that being unstable doesn't mean it's going to rise, doesn't mean it's going to sink. It means it's going to accelerate away from its original position. And that's in contrast to if that layer of the atmosphere were statically stable. When a layer of the atmosphere is statically stable, it means that if you lift an air parcel, it will tend to return back to its original altitude once you're done lifting it. Or if you lower an air parcel, it will tend to rise back to its original altitude once you're done lifting it. And that has a whole lot to do with how the wind profile is going to evolve. And that's kind of what we're going to focus on today, just to show you a couple slides we saw earlier. I mean, it makes sense that when if the wind down near the boundary layer is moving through a layer that is statically stable, it's going to be really hard for air that is slow near the surface of the Earth, just due to friction, to end up rising up higher in the boundary layer. And it's going to be hard for the faster winds that are up higher in the boundary layer to mix downward and mix in with that slow momentum down at the surface. So you end up with winds that are pretty weak near the surface and surprisingly strong up near the top of the boundary layer. On the other hand, if you have a lot of mixing going on in the boundary layer due to the plumes and thermals and things like that, turbulence and so on, well, it's awfully easy to mix high momentum air from up high down to the surface and take low momentum air from down near the surface and mix it upward. And you get a wind profile that has less wind shear. So far we spent a lot of time talking about the log wind profile, and we showed how it was tuned, if you will, by a couple of parameters like the U star, the friction velocity, or Z naught, the aerodynamic roughness length. And we saw there were realistic and unrealistic examples of it, but when we had appropriate combinations of U star and Z naught, we got profiles that were pretty realistic for the winds above a grassland, or above the ocean, or above a forest, or urban environment, or whatever. Now, strictly speaking, that log wind profile is only an appropriate approximation to the wind anytime the wind profile is occurring under statically neutral conditions. Now, statically neutral means a lot of things. I mean, we learned all about that in the first lecture of this module. We learned all about how, well, when the atmosphere is statically neutral, the environmental lapse rate, which we measure, is equal to the dry adiabatic lapse rate, which is just a constant. Another way to think about it is that the measured lapse rate of potential temperature, change in potential temperature with respect to height, is 0 when the atmosphere is statically neutral. Another way to think about it, if you're at a layer at the surface, is that it's going to be happening when our heat flux was equal to 0. Another way to think about being statically neutral was that was the set of situations in which a layer of the atmosphere has become well mixed. These are all different ways of saying how a layer of the atmosphere, we would describe it if it's statically neutral. And that's not going to be a terribly rare thing. It's going to be pretty much the normal thing during the day through much of the depth of the boundary layer. Maybe not the lowest few tens of meters, but most of the depth of the boundary layer, which extends, remember, up to a height of about 1 to 2 kilometers up, most of the depth of the boundary layer, most of the time, will be well described as being statically neutral. Here's a potential temperature profile that we have seen before in earlier lectures, and you can see highlighted there in yellow a big chunk of that temperature profile where the change in potential temperature with respect to height is 0. Temperature is neither increasing nor potential temperature is neither increasing nor decreasing with respect to height, and so that layer, much of that boundary layer there, is statically neutral. And in fact, that doesn't, I told you that had to be during the day, but actually, not exactly. Through most of the depth of the boundary layer, actually that trick works both day and night, but for very different reasons. During the day, that most of the depth of the boundary layer is going to be statically neutral because of all the mixing going on. We talked about how mixing results in a layer of the atmosphere that is statically neutral. And so during the day, when there's these warm plumes of air rising from the surface up through the depth of the boundary layer, cooler plumes sinking around it, etc., the layers are well mixed, and your boundary layer is mostly statically neutral. We call the Ekman layer during that time the mixed layer. Awkwardly, at night, it happens for different reasons. At night, it's not that there's much mixing going on. I mean, air near the surface is cold and dense and not wanting to rise. Air aloft is relatively warm because there's no diurnal cycle to the temperature of the air outside the boundary layer. That air doesn't want to sink. You might think that that would mean that the boundary layer would be stable, but actually it's not that. It's still statically neutral. And the reason is because even though it's no longer mixing, it's well mixed. It has been mixed. When we remember that analogy about the cake mix? Well, once it's been mixed, it doesn't tend on its own to stop being mixed anymore, and the egg goes off to one end of the dish and the flour goes off to the other and so on. Once the layer is actually pretty well mixed, it tends to stay homogeneous, even though it is no longer mixing. So at night, we have a different word for the boundary layer. Through most of the depth of the boundary layer, we call that the residual layer. It is a residual effect of the very large amounts of mixing that happen during the day. Meteorologists actually do not like these term Ekman layer because it's kind of lumping together two things that are actually happening for very different reasons. It just so happens they have the same effect. I mean, whether the boundary layer is actively mixing right now and we have the mixed layer, or whether it's at night and, well, there's no more mixing anymore, but the layer is so well mixed it doesn't really matter, it's the residual layer, you get the same effect of it being statically neutral, but for two very different reasons. So meteorologists hate that term, Ekman layer. They tend to either call it the mixed layer during the day or the residual layer at night. But even so, even though this big chunk of the depth of the boundary layer is statically neutral, if you take a look at the bottom of the boundary layer, right near the surface layer, that lowest 10 to 50 meters or something like that, you'll notice that the slope of the curve of potential temperature, and therefore the static stability of that layer, oh, it changes a lot over the course of a typical day. You can see how the curve can change quite a lot. And this is happening, of course, due to the flux of heat from the surface of the Earth into the atmosphere. During the day, the ground is warmer than the air, and there's a positive heat flux, H, out of the ground. And at night, the ground is generally colder than the air it's touching, and therefore there's a negative heat flux from the atmosphere down into the ground. And as you might recall from this slide that I'm just reminding you of from our stability lecture, the sign of the heat flux at the bottom of the layer is also a way of figuring out the static stability of the layer. So during the day, we should have that lowest surface layer, that lowest 50 meters or so, should be statically unstable. And at night, that lowest 50 meters or so should be statically stable. And that's actually what we're seeing there on that graph. Now the big question then, based on the topic of today's lecture, would be, how does this evolving profile of potential temperature and therefore of static stability modify the wind profile? We know we like that log wind profile. It's a good first guess. But what does the wind start looking like under these different conditions? Well, let's break this down and first do the statically stable conditions, and then we'll do the statically unstable conditions. So first we're going to talk about the statically stable conditions, which is like at night. And I just isolated that part of the graph down here, where we're going to focus mostly on the graph of potential temperature, the one on the right, versus height. Now, under these kind of statically stable conditions, we know that overall our wind profile should look a lot like the log wind profile. I mean, the basic assumptions that we made when we sort of hand-wavingly derived the log wind profile are still pretty good, and we still want, the wind should basically go to zero down near the surface. It should always be increasing with respect to height in the boundary layer, etc. And the basics of our assumption are hardly terrible, but, okay, there's also some problems now. I mean, when we were talking about that log wind profile, we were assuming that the conditions were statically neutral in that layer, that it was relatively easy to mix higher momentum air from up high in the boundary layer with lower momentum air from down low in the boundary layer, and kind of, easily transport high momentum downward and lower momentum upward to keep that kind of well mixed. But under these statically stable conditions, that's going to just be a whole lot harder. Remember, the atmosphere is going to be resisting vertical motions under these kind of conditions, under these statically stable conditions. That very slow-moving air down near the surface, that low-momentum air, is also cold and dense and not really wanting to rise in the under stable conditions. And that air above the surface, 50, 100 meters up, is a whole lot warmer. It's higher momentum, but it's hard to get it to mix downward to the surface and even out the wind profile. The result is going to be what we're going to call our second wind profile, which is the Loglinear wind profile. And just to take a quote from that reading that you're going to be doing from the Stoll textbook, if you haven't already, during statically stable conditions, such as at nighttime over land, the wind speed is slower near the ground but faster aloft than what you would expect from a log wind profile. That is a key understanding there to make sure you see what's going on with this Loglinear wind profile. Now I'm going to give you up there on the top right of the screen the equation for a Loglinear wind profile, and it might not seem all that illuminating until you take a peek back on the bottom left corner there. That is that equation that we used for the log wind profile. And when you take a comparison of the two, actually they're almost exactly the same. It's just that instead of multiplying by the log, we're multiplying by the log plus some other number that, well, actually there's only one new thing there, and that's that L. Alright, I mean everything else is the same. U star is the friction velocity, kappa is the von Karman constant, Z naught is the aerodynamics roughness length. The only thing that's new here when we're figuring out the wind speed U with respect to height Z is this L, which is the Obukhov length. Now, later on in the book, there's a whole bunch of understanding about Obukhov length and Obukhov theory and so on. He's one of the old dead white guys of science, and he was a big boundary layer guy. And he came up with this parameter L, the Obukhov length, and it's got a whole bunch of stuff in it. Most of like the U star and the kappa, we're old friends with that by now. G is just gravity. TV, that's just a measure of temperature. It's called virtual temperature. It's a little bit complex as to how you do it. If you substitute it in temperature, it would be fine. The only thing that's weird in here is that FHSFC, this is that weird way that Stoll works with a heat flux, but it's the same sort of idea of heat flux. It's positive when it's when the ground is warm and the atmosphere is cold. It's negative when the atmosphere is warm and the ground is cold. It just has different units. It's called kinematic units. Well, okay, we can think this through anyway. We can kind of think about what this means. But, okay, we're going to learn more about Obukhov theory and Obukhov lengths later. But, you know, to a good approximation, if you wanted to think about it, Obukhov length is sort of a measure of how deep that stable layer is. Okay, that was kind of where he was going with this, as he was trying to say, you know, it probably matters how thick that layer near the surface is that has become stable due to cooling at the bottom. So that's where he was going for with this. And so that's just where that term is there. And it's a length because it has units of meters and so on. Well, if you actually plot under the same conditions with regard to like U star and Z naught and so on, a log wind profile versus a Loglinear profile, you can see that they actually look kind of like what you were told in that important quote from Stoll. Namely that once you get more than a handful of meters above the ground, the Loglinear profile gets to be a lot stronger than the log profile. And that's just because the Loglinear profile is effectively insulated away from that friction at the surface. The air moving along at 60 meters above the ground has no way of feeling the surface. It doesn't mix with air from the surface because the situation is stable. The air at 60 meters tends to stay at 60 meters. The air at like 4 meters tends to stay at 4 meters. And as a consequence, it's really hard to take that relatively slow air near 4 meters and bring it up to like 60 meters and slow the air down. And you end up with a kind of much higher speeds above the surface and lower speeds down near the surface. Now, in this particular formation of the Loglinear wind profile, we don't actually see that business of how down, right near the surface the winds are going to be weaker. It's just not, this is a simpler parameterization of the Loglinear wind profile. But you can imagine that if we extended those graphs, all the way down to, like looked at them closer with my little PowerPoint magnifying glass, you'd see that the winds are actually getting a little weaker in the Loglinear wind profile near the surface. Campers know about this. If you like to go camping on a nice clear night, you know that once the sun sets, it gets really calm out, and the winds are really light, and it gets chilly down near the surface. You're experiencing that heat flux as the air is warmer than the ground, and the heat gets pulled by conduction from the air into the ground, and the air near the surface gets real stable. If you know what to look for with your campfire smoke, you can tell that, and so on. What you can't really tell very easily is, 20 meters up, the wind is roaring. Okay, the winds are actually stronger than during the day at 20, 30 meters up because of the log-linear wind profile. Down near the surface, the winds have basically fallen to zero, but 20, 30, 40 meters up, the winds are roaring a lot faster than they were during the day. In that sense, then, that's kind of good from a wind power perspective at night, right? Because your turbine is up plenty high. If anything, your turbine is up into the part of your turbine, the hub height might be 100 meters. You might even be up into the part of the atmosphere here where the wind speeds are greater at night than during the day. And so, actually, this is probably good news from like a wind power perspective in terms of how much power you'll be able to extract. So let's take a look at what we mean then for during the day. I mean, we again have this evolving profile of the potential temperature during the day. So therefore, we have an evolving profile of static stability, meaning that during the day, that surface layer, that lowest 10, 20, 30 meters, is going to be statically unstable in the during the day. So let's talk about statically unstable conditions. And this is going to be particularly case if on a sunny day, when the sun is shining on the ground, warming the ground up. We have a big flux of heat from the ground into the atmosphere as the ground warms up under the sun. Let's figure out a wind profile that should work here. Once again, we want to think about the log wind profile, because, the log wind profile is just such a handy tool. And again, the assumptions that we made behind it, things like the wind speed should be basically zero at the surface, the wind speed should be increasing with respect to height, that all seems pretty good. We just need to modify it to be like what we want to do for our unstable situation. Now remember, again, our log wind profile was assuming that the static stability was neutral for our layer. And while it wasn't going to be hard to move air parcels up and down in the boundary layer under those statically neutral conditions, the boundary layer wasn't really helping with that either. The boundary layer wasn't actively trying to encourage the motion of air parcels up and down. Under our statically unstable conditions, like what we're going to have in the surface layer during the day, now the heat flux is just cooking the atmosphere from below. We are transporting heat very rapidly from the ground into the lower atmosphere. We're producing volumes of warm air near the surface that rise in the form of these plumes, with sinking plumes of cooler air from up higher in the boundary layer all around it. Remember that visualization I showed you back in like the stability lecture where, you almost see, it's like a forest of plumes that are invisible to see with your naked eye, but they're happening all around you on this sunny day as air is being transported up and down in the surface layer, aggressively transporting momentum up and down in the atmosphere. When our surface layer is cooking like this, it's being heated from below, and there's these very active plumes acting in our boundary layer, we call that layer the radix layer, or the convective radix layer, and the wind profile that we're going to be seeing is called the convective radix profile. Now, there's at least two words here that might be making you uncomfortable. Convective. Okay, convection is about transporting air up and down, transporting a fluid vertically by like buoyancy and heat and things like that, okay? Warm air rising, cold air sinking, that's convective. Now, this is the convective radix layer. Radix is a tricky old weird word in science that means something like the root. It is in fact the same Latin phrase from which we get the word radish, for example, okay? It is the root of the convection. And so the convective radix layer down near the surface is like where these thermals that are mixing through the mixed layer are coming from. It is their origin, it is their source, it is their root, it is their radix, to use an old sciencey word. So this is the wind profile we get in the convective radix layer, hence it is the convective radix profile. And again, I'm going to just direct you to a phrase, that sentence that comes from that Stoll reading, that says, for statically unstable atmospheric boundary layers with vigorous convective thermals, such as occurs on sunny days over land, Wind speed becomes uniform with height a short distance above the ground. Wind speed becomes uniform with respect to height above the ground. I better look at the equation for that. No, feel free. Feel free. Go get that reading that I've got for you on Blue Line. I want you to do the reading. By all means, admire the equation at the top of page 81, but it's horrible. It's got all kinds of weird stuff, Deerdorf velocities and all kinds of weird stuff. It's not a useful equation in the sense that, like, I can look at the equation and see what the shape of this curve is going to be. It's just not a familiar form like that. And it's got all these weird exponents, and it's just not an easy equation to look at. Instead, let's admire a graph of a convective radix profile in the atmosphere. And okay, so here we have a graph of the wind speeds with respect to height. I didn't make one myself in Excel. This one is just scanned from the reading I gave you. And so on the x-axis we have wind speed, and on the y-axis we have height, and this is our wind profile, and well, it kind of looks like a log wind profile, but it's got some issues. I mean, like, look how over a big thick layer of the boundary layer, like from about, well, I don't know, 10 meters up to at least 100 meters up, the wind speeds are basically constant with respect to height. There's no wind shear here. du dz is 0. Again, making me very unhappy with your author's notation here. It's really should be partial u, partial z, but whatever. Okay, there's no change in the wind speed with respect to height. No wind shear. And this is, of course, due to all the mixing. I mean, there's an astonishing, aggressive mixing going on in this radix layer during this time. It's just constant turbulence, constant mixing, constant plumes of warm and cool air moving up and down, respectively, in this radix layer. We just end up with a constant profile of winds with respect to height. Any air that has a little bit faster, higher momentum than the air around it quickly gets mixed in. Any air parcel that has less momentum than the air around it quickly gets mixed in. So through most of the depth of the boundary layer, the wind speeds are constant with respect to height. Now, near the surface of the Earth, the wind speed is being shown is going close to 0. A more accurate way to think about it is down near the surface, the average wind speed, like the 10-minute wind speed or something, that will be not particularly high, but the wind will be gusty. When like a plume of sinking air from up above with higher momentum reaches the surface, you'll have a gust of wind as that passes. So the winds will be gusty, but it is true like a 10-minute average wind or something will not be particularly high under these kinds of conditions. Again, thinking about this in the context of wind power, most of your turbines are, like a traditional wind power turbine has its hub sufficiently high that, like that low wind speed right near the surface and gusty conditions near the surface and stuff don't really apply unless you're like talking about one of these more upright wind turbines or something like that. Most of our wind power applications will be up higher where, the winds will be fairly constant with respect to height. But again, we got now three different wind profiles in our atmosphere. And what we saw was that it was the diurnal cycle, the daily cycle of the heat flux at the surface that was driving changes in stability in that surface layer that ended up producing three different wind profiles. And that's pretty cool. And if you've got an instrumented tower or if you've got surface stations, you'll see these cycles happening and these changes in the winds happening, even though your wind turbine is probably higher up than this stuff in the atmosphere. All right, let's ask a couple quick questions before you go. Question 1. During the day, particularly if the day is sunny, we expect the layer of air near the surface to be A, statically stable, or B, statically unstable. All right. On a sunny day, what is the stability of the air near the surface? Make a choice for those two options and get a little feedback before you move on to question 2.